Welcome to the hangar floor. As aircraft systems become highly automated, maintenance remains the primary point of direct physical interaction between humans and aviation technology. Commercial air travel is exceptionally safe. Recent data from MIT places the risk of a fatal accident at roughly 1 per 13.7 million passenger boardings. That level of reliability is an engineering triumph. This graph tracks accident causes since 1903. Early machines failed constantly. We engineered those weaknesses out, seen in the declining blue line. As hardware improved, human error became the dominant vulnerability. The rising orange line shows 80% of accidents today result from human performance. The hardware is no longer the primary threat. Mitigating less than optimum human performance is now the most effective way to improve flight safety. In this environment, the technician functions as the final, most critical safeguard in the aviation system. This diagram divides security and safety. While both are essential, they involve different risks. Aviation security, seen on the right, deals with preventing deliberate, malicious acts like sabotage and terrorism. Aviation safety is the management of unintentional hazards. When a fatigue technician forgets to torque a bolt, it is not a criminal act. It is a safety hazard born from human limitation. This pyramid classifies unintentional errors using ICAO definitions. The yellow base represents incidents, minor errors or near misses where the outcome is safely managed. The orange tier covers serious incidents, where accidents are narrowly avoided. The red peak represents accidents, involving structural destruction or fatal injuries. The primary mission of human factors training is to identify and report the minor incidents at the bottom of this pyramid, stopping the progression before it reaches a fatal accident at the top. To manage those risks, we rely on ergonomics. This is the science of optimizing performance by adapting the environment to the human, rather than the other way around. This wireframe model shows why this is necessary. The human body has fixed biological and anatomical limits you cannot override. Using anthropometry, the measurement of human dimensions, we map exactly how much force a joint can apply, or whether an access panel is appropriately sized. The psychological constraints are just as rigid. The way the brain perceives data in low light, processes decisions under pressure, and manages short-term memory are fixed biological rules. This diagram breaks down how a safe system is engineered. It requires integrating physiology, psychology, and anthropometry into the physical workplace design. If the aviation environment requires a maintenance technician to work outside of these biological limits, error becomes inevitable. This diagram is the SHEL model. The outer blocks represent the system: software for manuals, hardware for tools, and environment for hangar conditions. The center block is liveware, the technician, placed at the absolute core, interacting directly with every other component. Notice the jagged edges. The blocks are not flush. These borders represent the interfaces, and mismatches at these connection points are where errors originate. This technical schematic compares a liveware hardware mismatch. In 1990, a fatigue shift manager replacing a BAC 111 windscreen bypassed the parts manual. Under poor lighting, he matched the old bolts to replacements by eye. He chose bolts that were microscopically too small. Mid-flight, the windscreen blew out, pulling the captain halfway out of the aircraft. This schematic illustrates a liveware software mismatch from Air Midwest Flight 5481 in 2003. The technicians lacked specific training, and the maintenance manual contained erroneous depictions of the trim drum. Following these instructions, they rigged the elevator control cables backward, resulting in a fatal loss of pitch control. Even the most skilled technician will fail if the tools or instructions they receive are inaccurate. The remaining SHEL interfaces govern your surroundings and your professional communication. In 1988, Aloha Airlines Flight 243 lost 18 feet of the cabin roof mid-flight. The investigation revealed a severe liveware environment mismatch. 2 experienced inspectors missed over 240 fatigue cracks because they were inspecting outside, at night, using flashlights while balancing on scaffolding. The final interface is liveware, representing communication and teamwork between colleagues during shift changes. This illustration highlights the danger of verbal handovers. In both the 1993 Excalibur A320 and the 1995 British Midland 737 incidents, technicians failed to produce written documentation for incomplete work. Human short-term memory is highly volatile. Relying on a spoken conversation to transfer the exact status of a flight control system is a lethal hazard. This technical diagram zeroes in on latent errors. During a tail strike repair on Japan Airlines Flight 123, technicians applied 2 separate splice plates instead of the mandated continuous plate. That error didn't cause a crash immediately. It lay dormant for 7 years and thousands of flight cycles before rupturing, killing 520 people. Environmental strain and communication breakdowns install hidden failures that can persist for years. Catastrophic accidents are almost never the result of one isolated mistake made by a single person. This illustration visualizes the multi-causal nature of accidents, known as the error chain. Accidents occur when seemingly minor errors align. A technician arrives fatigued, lighting is dim, a manual page is missing. Individually, these are managed risks. Together, they create a deadly sequence. However, the error chain is inherently fragile. The sequence relies on uninterrupted momentum. That gives the technician absolute power through a single intervention. If you identify just one mismatch, if you refuse to work without the correct lighting, or verify a manual before proceeding, the sequence collapses. You do not need to overhaul the entire aviation system to prevent a crash. You only need the discipline to stop the single domino immediately in front of you. To identify those dominoes, the industry uses risk assessment frameworks designed specifically for the hangar floor. This grid breaks down the PEAR model, the standard for maintenance task planning. Planners use people, environment, actions, and resources to guarantee that before a job begins, the physical steps are analyzed and the correct tools and personnel are allocated. The PEAP model is your immediate, frontline risk assessment tool, utilized directly at the aircraft. It is a pre-task checklist. Are procedures accurate? Is the environment safe? Is the exact equipment ready? Are the people rested and competent? You must verify the status of every PEAP category before starting the task. Modern aircraft are engineered for high mechanical reliability. The remaining 80% of aviation risk rests with human performance. Adhering to these frameworks ensures that the reliability of the aircraft is mirrored by the performance of the person who maintains it.